This session is about waves, which is in paper 2, and it's for combined and triple scientists. You need to know the definition of a longitudinal wave. Longitudinal waves include sound waves. Here, the vibrations are parallel to the direction the wave travels. You also need to be able to label a compression, a rarefaction, and the wavelength, which is the distance from compression to compression. Transverse waves include water waves and light waves. Here, the vibrations are at right angles or perpendicular to the direction the wave travels. You also need to be able to label a crest, a trough, the amplitude, and the wavelength of the wave. The amplitude of a wave is the maximum displacement of a point from its undisturbed position, which basically means it's the half height of the wave, is the distance from the middle to the top or the middle to the bottom of a wave. The wavelength is the distance from one point on a wave to the equivalent point on the next wave. So the easiest way to measure this is from crest to crest. The frequency of a wave is the number of waves passing a point each second. The time period or period of a wave is the time for one wave. And there's an equation that the period is equal to 1 over the frequency of the wave. This equation is on the sheet, so you don't need to learn it. The period is measured in seconds, the frequency in hertz, and we can lead up to an equation for wave speed, which is frequency times wavelength. V equals f lambda. V is the wave speed, measured in meters per second. F is the frequency, measured in hertz. And lambda is the wavelength, measured in meters. There is a required practical to measure the frequency, wavelength, and speed of a wave, and it involved a ripple tank. This is a tank of water with a little wooden bar dipping up and down into it to produce plane or straight waves at a regular rate. A light source is above it to project an image of the same size below the ripple tank. To measure the frequency, you place a marker under the ripple tank. You can video it to do this, but you need to measure the time it takes for 10 waves to pass, and you measure this with a stopwatch. You divide this time by 10 to get the time for one wave, and then use the equation that frequency is 1 over the period, or the time for one wave, to calculate the frequency in hertz. To measure the wavelength, you place a ruler under the ripple tank, take a photo of the waves, measure the length of 10 waves, divide by 10 to get the length of one wave, which is the wavelength of the wave. To measure the speed, you can measure the length of the tank from the wooden bar to the end, video a wave travelling across the ripple tank, and time how long it takes for the wave to travel across the tank. Then you can use speed equals distance over time to work out the speed of the wave. Alternatively, you can calculate the speed of the wave. Once you've found the frequency and the wavelength, you can calculate the speed using speed equals frequency times wavelength. The second part of the required practical was on standing waves. And they set up a string on an oscillator, as in the picture below, and they adjusted the frequency to get a standing wave. You may remember these. There were points on the waves that didn't move, as in the moving diagram below. The speed of the wave is determined by the weight on the end of the string and the length between the bridge and the oscillator. If you leave these fixed, the speed of the wave on a string won't change, but if you change either of these, it changes the speed. And speed equals frequency times wavelength. So if you leave the weight and the length the same, you can change the wavelength of the wave by changing the frequency. We set up different patterns, like the ones below. In the top one, the wavelength of the wave would be equal to 2 times the length of the string. In the second one, the wavelength was equal to the length of the string. In the third one, the wavelength was equal to 2/3 the length of the string. And in the bottom one, the wavelength was equal to half the length of the string. Waves can be transmitted, absorbed, or reflected. If it's transmitted, it's allowed to pass through the material. If it's absorbed, it's stopped and the energy is absorbed by the material. If it's reflected, it bounces back off the material. For reflection, the angle of incidence is always equal to the angle of reflection. You need to be able to draw the normal and the angle of incidence and reflection and be able to measure them with a protractor. A rough surface will scatter the light. It still follows the rule angle of incidence equals angle of reflection, but it hits each of the parts of the surface at different angles, so it gets scattered off in different directions. Refraction is the bending of a wave due to a change in speed, and a light ray will bend when it enters glass at an angle. First of all, we've got to look at why it bends. One side of the wave slows down as it hits the glass, whereas the other side keeps going at the original speed, and this is what causes the wave to change direction. Another thing to notice is the frequency of the wave doesn't change, so as the wave slows down, the wavelength gets smaller. When white light passes through a prism, the different frequencies or colours slow down by different amounts, and the more they slow down, the more they bend. Red light slows down the least, so is bent the least, and violet slows down the most, so is bent the most.